Hey everyone, and welcome to this explainer. Today, we're taking a fascinating journey to completely demystify the buzzwords of artificial intelligence. We're not just going to throw dry jargon at you, though. No, we're actually going to follow the birth and life of a machine learning model step by step. Okay, let's dive into this.
Here's our roadmap for today. We've got a logical four-part story. 1. The core building blocks. 2. How the machine learns. 3. Catching common mistakes. And 4. The final test.
Part 1. The core building blocks, gathering the raw materials. Because before a machine can learn, it needs a brain, and it needs textbooks. So before any machine can learn a single thing, it needs a brain, right? That's our model. Think of the model as an eager student setting up in the classroom. Now, at its core, a model is really just a mathematical structure of weights and parameters, just waiting to be optimized. There's literally no magic here. It relies entirely on advanced math to find patterns in information so it can eventually make predictions. But right now, our student doesn't actually know anything. It needs something to study.
And that brings us to the dataset. If the model is our student, well, the dataset is its massive, sprawling library of textbooks. Simply put, a dataset is a structured collection of input data. Whether we're talking about gigabytes of medical images, thousands of hours of audio, or millions of rows of text, this structured data is the absolute lifeblood of machine learning. Seriously, without it, our mathematical model has absolutely nothing to analyze, nothing to train on, and nothing to test its knowledge against.
And this brilliantly illustrates what happens when we actually open that textbook. The data is typically broken down into two main parts: features and labels. The features are the inputs, variables or attributes like a person's age, their income, or even the individual pixels in a photo. Think of features as the clues. Then on the right side, we have the label, sometimes called the target. This is the output the model is trying to predict, like whether an email is spam or not spam. It's the answer key. The model basically uses the features to try and guess the label.
Moving right along to Part 2, How the Machine Learns, the Education of an Algorithm. Now that we've got our student and our textbooks, here's the exact process flow we're covering today for the active learning phase. We just knocked out Step 1, gathering our input data. Now we're moving directly into Step 2, training the model, before we eventually validate it and send it off to inference.
So training is that rigorous studying phase. This is the actual process of teaching our model by feeding it all that data we just organized and then continually optimizing its parameters across multiple passes, which are called epochs. Essentially, the model looks at the features, takes a wild guess at the label, and then updates its internal weights based on how well it did. It just does this over and over again, digesting data and refining its internal math.
But listen, the model doesn't just study however it wants. The teachers, meaning the human programmers, have to set some strict ground rules for studying. And these rules are called hyperparameters. These are settings that control the model's behavior, and they're actually tuned manually by humans before the training even kicks off. A great example is the learning rate, which dictates exactly how quickly or slowly the model updates its weights. If it learns too fast, it completely skips over crucial nuances. But if it learns too slow, well, it takes computationally forever.
Now, as the model trains, it's definitely going to make mistakes. Enter the loss function. I want you to think of the loss function as the strict teacher's red pen. It mathematically measures exactly how far off the model's predictions are from the actual true values during training. The entire goal of our student during this phase is to make that loss function as small as humanly or mechanically possible. It minimizes the error through processes like gradient descent. Fewer red marks mean it's actually getting better at predicting that answer key.
All of this leads us to a really critical question. How do we know the model is actually learning the underlying concepts and not just, blindly memorizing the textbook? How do we know it's going to survive outside the classroom? That brings us to Part 3, Catching Common Mistakes, Correcting the Course. Because just like human students, machine learning models can develop some pretty bad studying habits.
Let's move to and see how this builds. To catch and correct these habits early on, we use a validation set. Remember that massive library of textbooks we talked about? Well, we purposely don't let the model read all of them during training. Instead, we hold a portion of that data back to act as a sort of practice quiz. This validation set is used to tune those hyperparameters we mentioned and make absolutely sure the model is genuinely learning. It's basically a safety net.
Now, what's really interesting about this slide is how it breaks down those bad studying habits into two polar extremes. On one hand, we have overfitting. This is when a model learns way too much from the training data.
I mean, it literally memorizes the textbook word for word, including all the useless noise and typos. And because it just memorized, it performs terribly on any new data it hasn't seen before. On the flip side is underfitting. This is basically the student who just slept through class. The model is way too simple and completely fails to capture the underlying patterns in the data at all. That practice quiz helps us catch and adjust for both of these extremes.
Once we've tweaked our model to avoid overfitting and underfitting, we evaluate its accuracy. And this is exactly what it sounds like, folks, the percentage of correct predictions made by the model. You can look at it as the final report card grade based on those practice quizzes. If the accuracy is high enough on data it wasn't directly trained on, our model is finally ready to graduate.
Which brings us to part 4, the final test, entering the real world. The training wheels are coming off. So the crucial point here is inference. Inference is the final exam. It is the real-world application of literally everything we've talked about today. It's the process of using our fully trained model to make predictions on entirely new, completely unseen data. The model doesn't have an answer key anymore, right? It doesn't have a loss function grading it in real time. It just takes in new features and generates a label. So when Netflix recommends a movie you end up loving, or your bank flags a fraudulent credit card charge, that is inference in action. Just take a step back and look at the incredible journey we've mapped out together. We started with a completely blank mathematical model. We gathered structured data sets full of features and labels. We put the model through grueling training, adjusted its hyperparameters, graded it with a loss function, tested it with a validation set to avoid overfitting, checked its accuracy, and finally unleashed it into the world through inference. We've just walked through the core machine learning terminologies, and you now understand exactly how they work together to power the tech we use every single day. So I want to leave you with this thought to ponder. The next time an AI seamlessly filters a piece of spam out of your inbox or recommends your next favorite song, I challenge you to ask yourself, which features did its inference engine use to accurately predict that label? Now that you know the life cycle of an AI model, I guarantee you'll start seeing these concepts operating everywhere behind the scenes. Thank you so much for joining me in this explainer. Keep asking those great questions, and I'll see you next time.